In the previous two lectures, we have discussed the classical theory and the quantum theory of dimagnetism. Now we are going to start to learn about paramagnetism. And in this case, we will also see, first of all, the classical theory of paramagnetism, and after that we will learn about the quantum mechanical theory of paramagnetism. Actually, when you talk about the classical theory of paramagnetism, the first classical theory for paramagnetism was provided by Langevin. So this is also called Langevin theory. But you will see the result obtained for the magnetic susceptibility of paramagnetic gases in Langevin theory actually fails in some particular situation, in some particular type of paramagnetic material. So Weiss has modified the Langevin theory so that it may explain the paramagnetism of such materials too. So you can say that there are two theories of paramagnetism, two classical theories. The basic theory was provided by Langevin, and then Weiss has modified this Langevin theory where this original Langevin theory fails. So after learning about the Langevin theory and the Weiss theory of paramagnetism, both are actually classical theory. After that we will learn about the quantum theory of paramagnetism. Okay. You know, whenever you talk about paramagnetic material, what does it mean? It means, the paramagnetic material has actually permanent dipole moment. It means the atoms or molecules of a paramagnetic material has already intrinsic magnetic dipole moment. But whenever you will take a specimen of the paramagnetic substance, the net magnetization is zero. Why net magnetization is zero? Because the atomic or molecular magnetic dipoles of a paramagnet are randomly distributed in absence of any external magnetic field. So when you say that H is zero, then these atomic dipoles are randomly distributed and the direction of the magnetic dipole moment are random, and so when you will find the net magnetic moment of unit volume of the specimen, then which is called actually magnetization, that is equal to zero. So in absence of magnetic field, due to the random distribution of atomic dipoles or molecular dipoles of a paramagnet, the net magnetization is zero. Okay, but what will happen when we apply the external magnetic field to magnetize the specimen? So let us say now H is not equal to zero. Actually, when external magnetic field is applied, then due to the external magnetic field, each atom of the paramagnetic material, which behaves like a tiny magnetic dipoles, experience torque, and that torque has a tendency to align the atomic dipole or molecular dipole along the line of applied magnetic field. Okay, and when most of the atoms or molecules which behave like atomic or molecular dipoles align along the magnetic field, then a net magnetization is developed. So then M is not equal to zero. In fact, when you place the specimen of a paramagnet in an external magnetic field to magnetize it, actually the magnetization is determined not only by the applied magnetic field, but there are two factors affecting this magnetization. First one is definitely this applied magnetic field, and as I have told you that this applied external magnetic field exerts torque on the atomic or molecular dipoles, and that torque has a tendency to align the atomic or molecular dipoles along the direction of the applied field. Okay? But at the same time, due to thermal agitation, the effect is just reverse. Magnetic field tries to align the atomic or molecular dipoles along the line of magnetic field, but due to thermal agitation, the reverse effect takes place. It means the thermal agitation works to disorganize the orderly state produced by the magnetic field. It means that due to this thermal agitation, the molecular dipole tend to not align along the line of magnetic field. Okay. So actually, at any given temperature, a kind of statistical equilibrium is reached with majority of molecules having their axes parallel to the field direction and hence contribute to the intensity of magnetization. Okay. So in equilibrium state, most of the molecules, not all, but most of the molecules are aligned on the line of applied magnetic field, or they orient themselves so that at least a component of their magnetic moment lies along the field, and so a net magnetization is developed. Okay. Actually, our aim is to find that magnetization first of all. You know, when once you calculate the magnetization, which means the dipole moment per unit volume, then dividing this m by h, you will get the value of the magnetic susceptibility of this material. Okay. So first of all, we are going to calculate the magnetization developed in a paramagnetic specimen when it is placed in an external magnetic field H, okay, to magnetize it. And for this, let us see. Here, I have shown in this figure that this is the direction of the magnetic moment mu of a atomic dipole or molecular dipole, and it is making an angle theta to the direction of the magnetizing field H. So in this condition, if theta is the angle between mu and H, then the component of mu along this H will be equal to mu cos theta. Okay, but this fact will be used sometime later. So for finding the magnetization, let us consider, we have considered a paramagnetic specimen and that has been subjected to the external magnetic field H. And we consider that N is the number of particles or number of molecules or atoms, you can say, in unit volume of the paramagnetic gas. For simplicity, I have directly considered the specimen of unit volume. Okay, so that you have not to take the volume of the specimen under account, and directly you will get the magnetization. Okay, because magnetization, you know, is the total magnetic moment induced in an specimen in its unit volume. So for simplicity, I have already considered there is a specimen whose volume is unity and that contains n atomic dipoles or molecular dipoles. Okay, and this mu is the dipole moment of each molecule. It means each molecule has same dipole moment, and I have assumed that that is equal to mu. Although you will see later that this is one of the drawback of this theory, because that due to thermal agitation, the dipole moment of each molecule cannot be equal to equal. that should be different. That should vary from minus infinity to plus infinity. But in the Langevin assumption, it has been assumed that each atomic or molecular dipole has same dipole moment, and that is assumed to be mu. And as I have shown that this mu makes an angle theta with the magnetizing field H. Okay. Now, when a magnetic dipole is placed in a magnetic field, okay, then due to the interaction between the magnetic field and the dipole, an interaction energy is developed in the dipole. If you can see, if this is the magnetizing field and this is your magnetic dipole having magnetic dipole moment mu, and theta is the angle between them. Okay. Then you have definitely studied in your course on magnetism in lower classes that the interaction energy or the magnetic potential energy developed in the dipole is given by E equal to minus mu dot H. This is a well-known formula for the magnetic potential energy. And since theta is the angle between mu and H, so this will be simply minus mu H cos theta. Okay. Now actually, as we are talking about the classical theory of paramagnetism, and the molecules of a gas classically obeys Maxwell-Boltzmann distribution law. You can watch my video on Maxwell-Boltzmann distribution law and its criteria. So definitely in Langevin theory, it has been assumed that the atomic or molecular dipoles of a paramagnetic gas obeys Maxwell-Boltzmann distribution law. Okay, and according to Maxwell-Boltzmann distribution law, the number of molecules or atoms having energy E at temperature T is given by this expression: A times exponential to the power minus E divided by Kb times T. Here E is the energy of each molecule and Kb is a universal constant, a well-known universal constant. It is Boltzmann constant. Okay. Since A is a constant, so you can say that this number n is proportional to E to the power minus E over Kb times T. Actually, this E to the power minus E by Kb times T, this is actually called the Boltzmann factor. Okay. Now, our aim is to find the number of total number of this paramagnetic molecules or paramagnetic atoms. Okay. And for this, let us consider that this Dn represents the number of molecules whose dipole moments fall within the solid angle d omega between two hollow cones of semi-vertical angles theta and theta plus d theta, as you can see in this figure. Okay. So actually, if you talk about this number Dn, whose magnetic dipoles lies in the solid angle d omega, which is between the two hollow cones, as you can see in this figure, having the semi-vertical angle theta and theta plus d theta. Okay. Then actually this Dn depends upon two factors. First factor is this Boltzmann factor, and another will be the solid angle. As the larger will be the solid angle, the probability of finding molecules in those region will be also larger. So Dn is actually proportional to E to the power minus E over Kb times T times d omega. Okay. So when you will actually remove this sign of proportionality, you have to put a constant. So K is the proportionality constant. And you can say that this Dn is equal to K times E to the power minus E by kb times t. But what is this E? You know, E is equal to minus mu h cos theta. So let us put the value of E here. So this will be e to the power minus mu h cos theta by kb times t. This outside minus sign is due to this formula, and energy is already negative, so here there is minus sign. Okay, and you know what will be this solid angle? You know how this solid angle will be defined. Actually, this is the annular region between the two hollow cones, and you know if here this d omega solid angle is formed, then this d omega is equal to area of that annular ring and divided by this r square. But what will be the area of this annular ring? You can see the width of this annular ring is equal to this much. Since this angle is theta, so this width will be r d theta. Okay, and since this is actually r, so radius of this inner ring will be r sine theta. You can see sine theta will be equal to that radius. Let us say this is AC. Okay, so this AC are divided by r. So AC will be equal to what? That will be r sine theta. So area of this annular ring will be its circumference times its width. Circumference will be 2 pi r sine theta, okay, and width is r d theta. So this is r d theta. So this is actually dA, and when you will divide this dA by r square, this r square will cancel, and d omega will be equal to 2 pi sine theta d theta. I think you have already an idea of this calculation of solid angle. So I have also mentioned it here that this d omega is equal to ds over r square. Instead of dA, I have written there ds, and ds will be equal to 2 pi r sine theta r d theta and divided by r square. And you can see that this r square will cancel, and this is 2 pi sine theta d theta. So instead of this d omega, I have written here 2 pi sine theta d theta. Okay. Now you have actually found the value of number of molecules or atoms of the paramagnetic gas in the solid angle d omega. Okay. So that if your aim is to find the total number of atoms or molecules in that unit volume of a specimen, then that n will be simply equal to integral of this dn. Okay, and we will integrate. The dn is defined here. Actually, this 2 pi k is a constant factor, so it is outside of the integral, and inside the integral we will have e to the power a cos theta sine theta d theta. Actually here a has been written for this. This is mu h over kb times t. For this I have assumed a. So the integrating factor will be actually e to the power a cos theta times sine theta d theta. Okay, and the limit for theta is 0 to pi. You can see. Now by method of substitution, you can easily evaluate this integral, and for this we consider that cos theta is equal to x. When cos theta is x, and then if you will take the differential, you will see that this will be minus sine theta d theta equal to dx. Okay. Now let us see what will be the limits when we will actually change the variable theta in terms of x. When theta is 0, you can see when theta is 0, what will be x? X will be cos 0, and that will be 1. And when theta is pi, x will be cos pi, which is minus 1. Okay. So when you will actually change the variable theta to x, then you have also changed these limits for x. Okay, so you can write n is equal to what? This will be equal to minus 2 pi k times integral of e to the power ax, because cos theta is x, times dx. Because dx, you can see this is minus sine theta d theta, so here is minus sign. Okay, now it just, you can see, if you will interchange the limit, this minus will become plus. So I have actually interchanged the limits, and you know, integral of e to the power ax, that will be simply e to the power ax divided by a. I have written a outside of this bracket. Okay, and limits are now minus 1 to plus 1, because I have changed this minus to plus, so limits has been interchanged. So after substituting the limits, you get that n is equal to 2 pi k over a times e to the power a minus e to the power minus a. Okay, but you know that sine hyperbolic a is equal to what? This is e to the power a minus e to the power minus a divided by 2. So this factor e to the power a minus e to the power minus a, that will be 2 sine hyperbolic a. So n is equal to 4 pi k over a times sine hyperbolic a. Actually, from here you can easily find the value of the unknown constant k. Actually, the purpose of this integration was for finding this constant k. And you can see this k will be equal to Na divided by 4 pi sine hyperbolic a. Actually, for calculating the value of magnetization, you will see we will need the value of this unknown constant k, which is actually this much. Okay. Now, our aim is to now find the magnetization, and for this let us see when the magnetic field is applied, then the atomic dipoles orient themselves at some angle to the magnetic field, although the field has a tendency to bring all the magnetic dipoles along its line of action. Okay, and for this, let us consider that this is one of the atoms or atomic dipole having magnetic dipole moment mu, making an angle theta with h. Okay, and when you will resolve this mu into its components, okay, then you can see this mu cos theta is its component along the magnetic field h, and this mu sin theta is the component of this mu perpendicular to h. Okay, okay, so mu cos theta is the component of mu along or parallel to h, and mu sin theta is component perpendicular. Now by symmetry, you can also take that there is an atomic dipole making angle theta which is in this direction. So the component of this mu parallel to the field h will be again mu cos theta, and its component in a direction perpendicular to h, that will be minus mu sin theta. This is along the negative y direction. Okay, so if you consider only two dipoles, then by symmetry you can see that the magnetic moment along the field gets added up. So the total magnetic moment along the field will be sum of this mu cos theta. Okay, and that is not equal to 0. Okay, but by symmetry you can see if we will add the components of mu in a direction perpendicular to h, that will be sum of this mu sin theta, and that will be equal to 0, because this mu sin theta will be cancelled by this minus mu sin theta, This is, for example, I have shown only two dipoles, but there are a large number of dipoles. So for each dipole, the component along H will be get added up, but the components of their magnetic moment perpendicular to the field will actually cancel one another. So I have written here, you can see, each of dn particles contributes a component of magnetic moment mu cos theta parallel to h, while by symmetry the components perpendicular to the field annul each other. Annul each other means cancel each other. Okay, and hence the magnetization, that is the magnetic moment per unit volume of the gas, will be found simply by finding the magnetic moment of dn molecules first of all, and when we will integrate that value, it means if you want to find the total magnetic moment of dn molecules, what will be that? You can see magnetic moment along the field of only one molecule is mu cos theta. Okay, and there are dn molecules, so the total magnetic moment of dn molecules will be mu cos theta into dn, and actually that is equal to dm, because this is number of molecules in unit volume market, and magnetic moment per unit volume is magnetization. So this is the elementary magnetization dm. Now when you will integrate this, then you will get the total magnetic moment of unit volume of the specimen. And you know, the total magnetic moment of unit volume is called magnetization. So magnetization M is found simply integrating mu cos theta times dn. Okay, and again the limits for theta is 0 to pi. Okay, now let us substitute the value of dn which we have actually obtained earlier. You can see this is the value of dn. Okay, this is the value of dn, you can see it here. Okay, so this is mu cos theta, and dn is k times e to the power mu h cos theta divided by kb into t times 2 pi sin theta d theta. You can see this minus minus will become plus, but as we have assumed that mu h over kb into t is a, so that has been replaced by a here, you can see. Okay, now again this integral will be found by the method of substitution, and for this here again we will take cos theta equal to x. Okay, and you know, when cos theta is x, you have seen here, then this minus sin theta d theta is dx, so dx will be dx is minus sin theta d theta. So replacing this variable theta by x, your result will be minus 2 pi mu k times integral from plus 1 to minus 1. We have seen the how we can find the limits here, and this mu cos theta, okay, mu is outside, but cos theta is equal to x, and e to the power a cos theta, but cos theta is x, so this is e to the power ax, and instead of this sin theta d theta we will write minus dx, so minus sign is here and dx has been written here. Okay, now you can see the integrand is actually the product of two functions. First function is x and another is e to the power ax. So we must follow the method of the integration by parts for simplifying this integral. Okay, And you know x is algebraic function and e to the power ax is an exponential function. So from the formula of Euler, you know, we must take the algebraic function as first factor or first function and the exponential function as the second function. Okay, and then apply the rule of integration by parts. Okay, now again this minus sign has been changed to plus by replacing or interchanging the limits. Okay, the lower limit we will make upper and upper limit will be made lower. Then this minus will become plus. So this is 2 pi mu k. Now let us see. Remember the formula for integration by parts. You know, according to this formula, we have to write first function, which is x, times integral of second function. E to the power ax is second function. Its integral will be e to the power ax by a, and limits are minus 1 and plus 1. Okay. Then we have to write minus integral of differential of first function. What is first function? X. And its differential will be 1. And then integral of second function, that is e to the power ax over a. Okay. Now let us simplify this result, and the simplification is very easier. You can see m will be 2 pi mu k. Now when you will put the upper limit, see here, x will be 1. So this is 1 times e to the power a over a. And when you will put this lower limit minus 1, then this will be minus 1 times e to the power minus a by a. But when you will subtract the second term, minus minus will become plus. So after substituting the limit, the first term is e to the power a plus e to the power minus a over a. Okay. Now let us simplify the second term, which is this. Again, we have to integrate e to the power ax. That will be e to the power ax by a. 1a is already present, so in denominator there will be a square. Okay. So this is minus 1 over a square e to the power ax, and limits are minus 1 and plus 1. Okay. And after substituting this limit, your result is like this. This is 2 pi mu k times e to the power a plus e to the power minus a over a, and minus e to the power a minus e to the power minus a over a square. Okay. Now you know that this cos hyperbolic a, this is equal to e to the power a plus e to the power minus a divided by 2. Okay, divided by 2. So instead of this e plus a plus e to the power minus a, you can write 2 cos hyperbolic a. Okay, 2 cos hyperbolic a. And instead of this e to the power a minus e to the power minus a, you can write 2 sin hyperbolic a and divided by a square. Now you have seen what is the value of k. I have already calculated the value of k earlier, and that will be needed there. This is the value of k. So let us substitute this value of k2 in this equation. So you can see this 2 pi mu factor is at it, and instead of k we will write Na divided by 4 pi sin hyperbolic a. This is the value of k. Okay. Now you can see when we will multiply by this a, or you can take this a as a common factor from this denominator, then this a in numerator will cancel out. Okay, and divide by this sin hyperbolic a to the terms inside the square bracket. Then this first term will be cos hyperbolic a divided by sin hyperbolic a, and that is equal to cot hyperbolic a. and in second term sine hyperbolic A will cancel out, and so this is only minus 1 over A. Okay, and 2, when you will take 2 as a common factor, 2 times 2 will be 4, and here this 4 will actually cancel. These get cancelled. Okay, this A and this get cancelled. So finally we get that the magnetization M is equal to mu n times cot hyperbolic A minus 1 over A. Okay, actually instead of this cos hyperbolic A minus 1 over A, we write L of A. Actually this L of A, which is equal to cot hyperbolic A minus 1 over A, this is the well-known Langevin function. This is called Langevin function. Okay. So finally we get the expression for M, which is magnetization, that is the magnetic moment per unit volume. Okay. In fact, you can see this. What is this mu n actually? N is the total number of molecules or atoms, or you can say atomic or molecular dipoles in unit volume of the substance. Okay, and mu is the magnetic dipole moment of each molecule or atom. Okay, so when all the atoms are along the line of H, then what will be the total magnetic moment of unit volume? That will be simply mu into n. So this is actually the maximum magnetization produced in the specimen, and this maximum magnetization will be produced when all the atoms or all the molecular dipoles align along the applied magnetic field. Okay. After that, even when you will increase the strength of magnetic field, since there is no magnetic dipole left which are not along the line of action of H, so nothing will change after that. So this is also called the saturation magnetization. Okay, this is the maximum or value of the magnetization produced in this specimen. Okay, so as you can see, I have written here that this mu n is equal to mu s, and it represents the maximum possible value of magnetization when all atoms have their magnetic axis along the applied field. Okay, and this is called saturation magnetization. So if you write Ms instead of this mu n, then M is equal to Ms times L of A. Okay, I think we have clearly understand that this what is this Ms and when it will occur. Okay, now you can see that actually this M depends on this Langevin function L of A, and L of A depends L of A means L is a function of A, and you have seen that A is equal to mu h divided by Kb times T. You have seen. So A actually is a function of H and T. So definitely you can say that this magnetization will depend on temperature and the magnetizing field H. And if magnetization depends on temperature and magnetizing field, then susceptibility chi, which is simply M over H, that will also depend on temperature T and magnetization H. So you can say that what will be the magnetization, what will be the magnetic susceptibility of a paramagnetic substance? That is a function of temperature and magnetizing field. So actually we will consider actually two special cases, two particular cases, and discuss the magnetization or the susceptibility in that very two conditions. So let us see the two very important cases under which we will discuss the magnetization and the susceptibility of this material. In first case, we consider that temperature is low but field is very strong, very high. If temperature is low and field is high, in other words, you can also say that we are going to consider mu h is much greater than kb times t. Mu h is much greater than kb times t. It means h is very strong, very large, but t is very small. Let us see what will be the Langevin function in this condition. Because Langevin function decides the value of m, because ms is a constant, this is mu times n, and La will vary in accordance with A and A varies in accordance with H and T. So we have to find the value of Langevin function under the condition when mu h is much greater than kb times t. Actually, when mu h is much greater than kb times t, you can see that this A will be much greater than 1, because mu h is much greater than kb times t. Mathematically, you can say that we will evaluate the value of Langevin function under the limiting condition when A is very large. Mathematically, we will write A tends to infinity. Then what will be La? Okay, and once you get the value of La in this limiting condition, you can say what will be M, what will be chi. Okay, so let us evaluate it. So the limiting value of Langevin function L of A when A tends to infinity is what? You can see this will be limit A tends to infinity, and you know the expression for Langevin function is cot hyperbolic A minus 1 over A. Okay, but cot hyperbolic A, you know, this will be e to the power A plus e to the power minus A divided by e to the power A minus e to the power minus. This is the expression for cot hyperbolic A, and 1 over A is at each. Now, before putting the limit, we have to actually free this expression from the indeterminate form, and for this we take e to the power A as a common factor in both numerator and denominator. And you can see when you will take e to the power A as a common factor, the remaining factors will be 1 plus e to the power minus 2A, and also in denominator this will be e to the power A times 1 minus e to the power minus 2A. This will cancel out. Okay. Now substitute the limit. You can see when we will put the limit in numerator, there will be 1 plus e to the power minus infinity divided by 1 minus e to the power minus infinity and divided by 1 by infinity. You know, e to the power minus infinity is 0. So this will be simply 1 plus 0 divided by 1 minus 0 and divide minus 0, because 1 upon infinity is 0. So this is simply 1. Okay, so this is 1. I have actually written it here, you can see. So Langevin function comes out to be 1 in this limiting condition when you consider that magnetic field is very strong and temperature is very low. In that condition, Langevin function is 1. And so M is equal to simply mu n, and that is equal to ms, because you know M is equal to ms times L of A, but L of A you have obtained is equal to 1, so M will be simply equal to ms. In this condition, there will be saturation magnetization, and the physics behind it is obvious. What you have considered? T is very small, T is low, it means there will be negligible thermal agitation. Okay, negligible thermal agitation. But H is very strong. It means each atomic or molecular dipole will experience a strong torque, and so that those torque will bring the dipoles along the magnetic field. Okay, and due to the very low temperature there will be a little thermal agitation. That's why in this physical condition we can say that almost all the atoms or all the molecular dipoles will align themselves along the line of action of the magnetizing field, and that's why M is simply equal to the saturation magnetization. Okay, so I have written it here. You can say that thus at low temperature and in very strong magnetic field, paramagnetic substance acquire saturation. Okay. Now we will consider the next important case, which is just reverse of the first case. Now we consider that temperature is large but field is small. Just reverse of the first case. When temperature will be large and field is small, the condition, this condition you can say that is mu h is much smaller than kb times T. Okay, and so in this case what will be A? A is mu h upon kbt. Since mu h is much smaller than kbt, so you can say that this A is much smaller than 1. And you know, if a number is much smaller than 1, mathematically that means A is tending towards 0. Okay, A is tending towards 0. So in this condition we have to evaluate the value of Langevin function under the limiting condition A tends to 0. So let us see. Limit A tends to 0 L of A. And this is the expression for L of A, you know. And we impose this limiting condition A tends to 0 on it. Okay. Now since A is very small, and you know, when we expand e to the power x, or you can say e to the power plus minus x, then this is 1 plus minus x plus x square by 2 factorial plus minus x cube by 3 factorial and so on. Okay. But when x is very small, here A is very small, A is tending to 0, then we will neglect the higher power term. The terms containing the higher power of x can be neglected if x is very small. Okay. Since here A is very small, it tends to 0, so we can expand this e to the power A up to these 3 terms. 1 plus A square by 2 factorial. 2 factorial is simply 2. And similarly, this e to the power minus A, this will be 1 minus A plus A square by 2. I have neglected all the terms after this. Okay. And similarly in denominator, now e to the power A is expanded up to the 4th term. This is due to the mathematical region. 1 plus A square by 2 factorial, which is 2, plus A cube by 3 factorial. But you know 3 factorial is equal to 6. 3 into 2. Okay. And similarly e to the power minus A is expanded like this. Okay. And the last term is 1 by minus 1 by A. Now you can see this A and this A will cancel out, and this 1 plus 1 will be 2, and A square by 2 plus A square by 2, this will be 2A square by 2. You can see. And now in denominator you can see this 1 and this 1 will cancel due to this minus sign, and A will be added. Minus will become plus, so this is 2A. Okay. and a square by 2 and this minus a square by 2, this will cancel out, and a cube by 6 plus a cube by 6, this will be 2a cube by 6. Okay. Now we will simplify this RHS to some extent, and after that we will substitute the limit. You can see here this expression can be written like this. This is 1 over a times 1 plus a square by 2, okay, times 1 plus a square by 6 whole to the power minus 1. Actually this factor in the denominator, a has been taken as a common factor, and the 2 will actually cancel out, and 1 plus a cube by a square by 6, this is brought in numerator, so the power is minus 1. Okay. Now a is very small, and you know by binomial expansion that this 1 plus x to the power n, this is almost equal to 1 plus nx if x is much smaller than 1. Here a square is very small, it tends to 0. So when we will make the binomial expansion, then we will consider this first order approximation. And considering that first order approximation, this will be 1 minus a square by 6. Okay. Now let us multiply these two factors. You can see this is 1 minus a square by 6 plus a square by 2 and minus a4 by 12 and minus 1. Now this minus 1, this 1 will cancel out. Now a is very small, it is tending towards 0, so a to the power 4, this term will be negligibly small. So let us neglect the term a to the power 4 divided by 12. And after neglecting it, you can see we will take this a square by 2 as a common factor, and this will be equal to a square by 2a times 1 minus 1 over 3. So here this a will cancel out, and this is actually 2 by 3. This will be 2 by 3, 2 by 2 into 3, 2a by 2 into 3. Here 2 and 2 will cancel out, and so this is simply a by 3. So in this case, when temperature is very large and field is weak, in this condition you can see the Langevin function comes out to be a by 3. Okay, and therefore you can write the expression for magnetization M, which is ms times L of A, but L of A is in this condition a by 3, so M is ms times a by 3. Again, you know ms is equal to mu n and a is equal to mu h over kbt. So this is mu n times mu h over 3 kbt. Okay, and therefore you can say that M is equal to mu square n h divided by 3 kbt. So this is the expression for magnetization in this particular case when you have considered that temperature is very large and the field is small. Okay. Now after knowing the value of M, easily you can find the value of paramagnetic susceptibility. From the definition of susceptibility, you know chi is equal to M over H. And see here the expression, this H will cancel out, and so the expression for chi is n mu square over 3 kbt. And this result is also written as chi equal to C over T. Actually C is equal to this much. Sorry, not T. T should be not here. Okay. C is equal to n mu square over 3 kb. Actually, this is known as Curie's constant, and this equation A4 is known as Curie's law. Okay, and so you can say that for a paramagnetic material, according to Curie law, chi is inversely proportional to T. It means with rise in temperature, the magnetic susceptibility of a paramagnetic substance decreases. Okay. Now, let us see this figure. Actually, in this figure, I have shown the variation of Langevin function L of A in against of A. Okay. Actually, when A is equal to 0, then Langevin function will be 0. You can see the expression for Langevin function. This Langevin function is equal to this much. Okay. And actually when A is 0, then Langevin function is 0. Okay. But as the value of A increases, the value of Langevin function increases non-linearly. And finally, its value A becomes constant up when it rises to the value 1. It means the highest value of this Langevin function is equal to 1. And when it is 1, you have seen earlier that in this situation, when you have considered that temperature is very low and the field is very high, then Langevin function is actually equal to 1. Okay, so finally it gets saturated. But in the very beginning, when A is very small, then it varies almost linearly. Okay, so you can see I have written that variation of L of A in against of A for a small has been shown here. For a small value of A, the curve is sensibly linear and coincides with the tangent to the curve at the origin. If you will draw a tangent here at the origin, then this tangent will coincide to this LA curve, but when A is small. But when A becomes larger, you can see that this curve is deviated from the tangent. Okay. So this is the manner in which this Langevin function varies with A. Okay. Actually, we have learnt clearly by the classical approach applying the Maxwell-Boltzmann distribution law, which is actually a classical theory, the Langevin theory of paramagnetism. But as I have told you earlier that there is some drawback of this theory, and what are those drawbacks you can see. Actually, I have mentioned here that this theory failed to explain the complicated type of dependence of susceptibility upon temperature exhibited by several paramagnetics. For example, compressed and cooled gases, solid salts and crystals, etc. It means according to Langevin theory, the magnetic susceptibility has a very simple relation with temperature T. It is just inversely proportional to T, which is called Curie's law. But actually, can you say that this variation is always obeyed by all paramagnetic materials? Answer is no. Actually, as I have given here some example, if you will take the compressed and cooled gas, or you will take a solid salt, or you will take the paramagnetic crystals, then you will see that this chi is not inversely proportional to T. But how this chi will depend on T, that manner is very complicated. So you can say that this theory fails in explaining the temperature dependence of this susceptibility in case of this type of paramagnetic materials. Okay. Again, it is seen that this theory does not throw any light on the intimate relationship between para and ferromagnetism. Is there any relation between paramagnetism and ferromagnetism? From Langevin theory, we cannot conclude, we do not get any information that para and ferromagnetism are related. But when we will study Weiss theory, then you will see that actually the paramagnetic behavior and ferromagnetic behavior are related to one another. Actually, the transition of ferromagnetic material in the state of paramagnetic material is just an example of second order phase transition. Okay. So as I have told you earlier that this Langevin theory is a classical theory, but it has some drawback. So actually, for the removal of this drawback, Weiss has proposed another classical. Weiss theory is also a classical theory, but following the Weiss theory, we will actually see how the variation of this chi with T for this type of materials can be explained. Okay, and so in next lecture we will see the another classical theory of paramagnetism, which is called Weiss theory. Okay, thank you very much.